from the previous chapters or any past paper questions or anything you'd like to discuss? Nope. Okay. Okay. So let's begin. Now, for example, so we were done with moments, okay, but we've got to do pressure and density before we can do complete questions of moments because most of the questions for moments are very, very linked with other chapters. Okay. So let's start with a very basic idea of what is density. Yes. What is what does density really mean? Does it mean that something is more heavier than something else? Or something is lighter or something has a greater weight? No, not exactly. Density, the basic idea is how much mass you have, how much mass you have per unit volume. The basic idea is, for example, if you have a metal ball which has a radius of 10 centimeters and you have a plastic ball which has exactly the same size, but the plastic ball weighs 2 kgs, but the metal ball weighs 10 kgs. So do you see that the metal ball is more dense? Why? Because the metal ball has more mass. This has more mass in the same volume, has more mass in the same volume. That's basically what density is, in the same volume. So how would you define the formula for density? Density is basically equals to mass per unit volume, right? So how much mass you have per unit volume. For example, if the density is 1000 kg per meter cube, this means in 1 meter cube of in 1 meter cube volume, the mass present is the mass is equals to 1000 kgs. That's it. That's what density means. That means if you take out a 1 meter cube chunk of whatever material you have, then this chunk is going to weigh 1000 kgs, right? Now, if you take out another chunk which has a lesser density, that means in the same chunk, it's going to have a lesser or smaller amount of mass, right? So how do you calculate the density of this ball? Now, if this is a 3D ball, right? It's a sphere. So that means, how can you calculate the density of this ball? So density is equals to mass per unit volume. We know what the mass is. We know the mass is 10 kgs, but what is the volume? It's not 10. The volume of a sphere, you've got to memorize that. Volume of a sphere is 4 over 3 pi r cube. Okay, make sure you remember that. So what is r? So 4 over 3 pi into r is 10 centimeters. So 10 into 10 to the power minus 2, and then you cube it. So the volume turns out to, let's see what it turns out to. Keep your calculators with you. We're going to do lots of calculations. 4 over 3 into pi 10 into pi minus t cube. Okay. So the volume of this ball is 4.18 into 10 is power minus 3 meter cube. Okay. Now, that means that the density must be equal to 10 divided by 4.18 into 10 to the power minus 3. So that means if I do 10 over this value, then that means the density is equals to 2380 kg per meter cube. That means if you take out a meter cube, right? If you take out a volume which is equal to 1 meter cube of this ball, then then it is going to have a mass of 2380 kgs. Okay. Now let's do the same for the plastic ball. Now the plastic ball in the same mass has a density of mass over volume. It has a mass of 2 kgs, right? But do you see it has the same volume because it has the same radius? When you plug it into the volume is equals to 4 over 3 pi r cube, then you're going to get the same value as we got earlier because everything is the same. 4.18 into 10 to the power minus 3 meter cube. So density is equals to 2 divided by this value, which means that, let's do what that is, 2 over 4.18 into 10 to the power minus 3. Yep, so this has a density of 478 kg per meter cube. Okay, now in this example, it was very clear to figure out which one is going to be denser. So, right, so this is more dense. Clearly, we can clearly see that it has a greater density because it literally has more mass for the same volume. Okay, so that's how we calculate density. Now, in some cases, it might not be as apparent. For example, You have this cylinder and you have this cylinder. Okay. Now this has a mass of 5 kgs and this also has a mass of 5 kgs. Okay. But they have different lengths and sizes. This is a longer or thin cylinder, and this is a shorter, thick cylinder. How do you know which one is more dense? Then again, you've got to, plug in the formula for density. Density is equals to mass per unit volume. What is the mass of the cylinder? That's 5 kgs. What is the volume? Now, keep in mind, the volume of a cylinder is equals to pi r square into L. Okay. Why? Because, think about it. If you have a cylinder, what is the surface of that cylinder? It is a circle, right? So the area of a circle is pi r square. And if you multiply that times the length, right? For example, L times. If you keep doing that over and over and over again, then isn't this basically a cylinder, right? That's a cylinder, right? So that means if you multiply pi r square times the length, that's basically the volume of a cylinder, because we can literally see that if you keep filling up, pi r squares and pi r squares and pi r squares over and over again, then that is basically, it's going to make up a cylinder. Okay, so that's where the formula of a cylinder comes from. Okay, then volume of the cylinder. Now, this is going to be pi into what is the radius? The radius is actually going to be 2. Okay, so that means that's 2 centimeters, because this is equal to diameter. So 2 into 10 to the power minus 2 squared into what is length? 10 centimeters. Again, switch it. 10 into 10 to the power minus 2. Okay, let's see what that turns out to. 5 over pi into 2 into 10 to the power minus 2 squared into 10 into 10 to the power minus 2. Oh, that's very dense. So that
So,
means, yes,
so why are we doing 10 to the power of minus 2 again?
because the units are in centimeters, whereas we always make sure that they're in SI
Oh,
units,
yeah. Yeah.
right? So 1 centimeter should equal to 1 into 10 to the power minus 2 meters. Okay, you can use whatever conversion, method you like. I just added 10 to the power minus 2. Okay, you can also do divide by 100. It's the same thing. 10 centimeter divided by 100 is basically the same thing. Okay, so 40,000 kg per meter cube. Okay, so this is a really, really heavy material. Okay, that means in 1 meter cube of this cylinder, it's going to have 40,000 kgs. Now let's check it out for the thicker cylinder. Again, density is equals to mass per unit volume. What is the mass? That's 5. What is the volume? Now, again, you do volume is equals to pi r square times L. Now, in this case, the radius is actually 10 centimeters. So 10 into 10 to the power minus 2 squared multiplied by what's the length in this case? Now it's 4. So 4 into 10 to the power minus 2. Let's check what that number is. So 5 over pi times 10 raised to power minus 10 minus 2 squared into 4 into 10 to the power minus 2. Okay, so clearly, second. Ah, so this has a density of 3978, or let's just round that up to 40,000, 4,000 kg per meter cube. So clearly we can see that this cylinder has a much shorter density. Why? Because in this case, what we see is if density is equals to mass per unit volume, right? If you increase the volume by keeping mass the same, then obviously density is going to fall, because you have more volume for the same amount of mass, right? So it's less dense. It has
So,
lesser mass per unit volume. Yes.
for the volume, how
Hmm.
would R be 10?
Uh, oh, so right. Sorry, that was 5. So
Oh,
this was
okay.
supposed to be 5. Yep. So this was the diameter. This was diameter. So R is supposed to be 5 centimeters. Yes. Thanks for catching that. So that means this is supposed to be 1 second. So 5. Yep. So that's going to be 15,000. That is cool. That made such a big difference. Of course it did. So 15,000 kg per meter cube. But we can clearly see by calculation that this cylinder is supposed to be more dense. Okay, sounds good. Any questions so far?
No.
Okay, all good. Now, we're just going over like very few IGCSE basics. Now, of course, states of matter, solid is the most dense, right? Then liquid is slightly less dense. This is average. Then gas is very, very, very less dense. Why? Because you literally have, if you go from left to right, then the density is decreasing. Why? Because you can literally see that you have lesser particles, thus lesser mass in the same amount of volume, right? Imagine these are all the same cubes, and in those same cubes, you have lesser mass. So obviously, it's going to be lesser. Okay, you can read out these densities of some random materials later on. Not really important. Okay, okay, we can skip over this now. Let's go get over to the most important part: pressure. Now, for example, you have someone wearing shoes on ice, on thin ice. And for example, you've also got someone who's wearing these pretty heels, but who is most likely to die? It's probably the one with heels. So heels are not a great idea if you are, going on to thin ice. Now, how do you figure out which one is more likely to crack the ice? Now, we're supposed to like have a very important numerical value for that, and that's exactly what we call pressure, right? That's pressure. How do we define pressure? Pressure is basically how much force is applied, how much force applied per unit
So
area. Yes. Are you saying something?
no, I was just saying like it's how much
Hmm.
force applied on a certain area.
Exactly. Pressure is equals to force per unit area, and the units are supposed to be pascals, pascals. Okay, and or the base units would be Newton per meter square. Okay, now for example, we know that ice actually breaks at 1 megapascal of pressure. Okay. So 1 megapascal means 1 into 10 is to power 6 pascals. The ice is likely to break. Okay. Now, how do we figure out what is the pressure of this person on ice and what is the pressure of this person on ice? Okay. Now, you always have to look at what is the contact area. If you think about it, if you are on ice, right, it is much better to lay down on ice and spread yourself out, right? Because you have more weight distributed over. Sorry, you have the same weight distributed over larger area, right? You're going to spread yourself out on ice, and because your weight is the same, you are going to spread out your weight onto a larger area, right? If you're standing up, then that means all your weight is supporting by your feet. Now, what is the contact area for your shoes? So your weight is being applied over all of this area, right? This is your weight, and your contact area is this one. This is your contact area, the sole of the shoes. Okay, now it's been calculated. So by the way, this is equals to weight, weight, weight. You've got like tiny pieces of weight that are applying a force onto the ground. Now, can you calculate how much force is being applied per unit area? Let's check. What is your weight? Let's say 60 kgs, right? So 60 into 9.81, force over area. How much force are you applying onto the ground? That is 60 into, no wait, 60 divided by 9.81. 60, oh right, we've got the mass. So 60 mg, right? So m is 60 and 9.81 g. What is the area? Now the contact area with the shoe and the ice is 0.02 meters square. Let's check what that is. So 60 into 9.81 divided by 0.02. Okay, so that means the pressure is actually equal to 29,340 pascals. Now, what does this number really mean? That means that your shoes are applying, or you are applying, on average, 29340 newtons of force per unit area. Okay, then let's do it for the lady. Let's calculate the pressure due to her. Force over area again. What is the force? Same weight. Okay, so 60 into 9.81. But do you see that the contact area that she has is much smaller. She is concentrating her weight over a very small area, right? On this part and on this part and on this part, right? She's concentrating her weight. It's not very spread out at all. So all of the weight of her mass is being concentrated over very, very tiny areas, whereas the shoe was spreading it out much more. And you even see that the contact area of the heel with the ice is 0.00001 meter square. So obviously that means the area in contact is very small. That means the same weight is going to be concentrated over a smaller area. Let's check what that is. So 60 into 9.81 divided by 0.00001. Okay, so clearly that turns out to 5.8 into 10 raised to power 6 pascals. Now this is a really high pressure. And is that larger than 1 megapascal? Yes, it is. That means that heels will break ice. Heels will break ice, right? So that's basically the big idea, that you've got to figure out how much force you're applying per unit area. Now, in this case, this would mean that the heels are applying 5.86 into 10 raised to power 6 newtons of force on 1 meter square of area. What that means is, of course, we calculated it for this like 0.0001 meter square. But if you take that out as 1 meter square, okay, so that means if this is 1 meter square, 1 meter, 1 meter, if this is 1 meter square, then the force on this entire 1 meter square would have been 5.8, or, just round it off to 6. 6 into 10 is power 6 newtons, right? So that's basically 6 million newtons, right? So there is a force of 6 million newtons being applied onto a meter square. Okay, any questions so far? Yes, Hania, all good? Kaima?
Yes.
Okay. Yes, Kaima, can you hear me?
Yes, I can hear you.
Okay, all good, all just IGCSE stuff. Yes, Ares, all good?
Yeah.
Okay, let's move on. Now, let's talk about pressure in fluids. Now, I'm sure you've seen in some kind of video that if you have a bottle and you poke holes into it in 3 levels, what happens is that at the top, the stream is going to be very weak, right? It's going to fall down, but it's not going to be very strong. But as you go down, does the streak get more powerful or weaker? What do you think, Anya? What happens to the streak over here, the second hole? Does it get stronger or does it get weaker?
It gets weaker.
It gets weaker. I want you to try that out now. It gets stronger. It is going to get stronger. I'm sure you can even try that. Let me see if I have a YouTube video for that. 1 second.
So it gets stronger because like there are more water molecules over there, right? Like at the
Okay.
bottom.
Not exactly. Now let me show it to you. 1 second. Ah, here it is. Here it is. Check it out.
Place the tray at the base of the bottle and quickly remove the tape. The water pressure is the least at hole A. the water spurts out the shortest distance. There is less water pressure at hole B. The water spurts out at a shorter distance. The water pressure at hole C is the greatest. The water spurts out the furthest.
Right? So we can clearly see that if you poke holes, as you go, as you increase in depth, as you keep falling down, right? 1 second. As you go down or increase in depth of the bottle, right, what happens is that the stream gets stronger, right? So that means hole A, hole B, and hole C. Hole C has the strongest streak, right? So this has the strongest, this has strongest stream. But why is that so? It's not exactly RS because of more molecules. The molecules are mostly spread out equally. The thing is, think about it. If you were to divide this bottle into 3 pieces, okay, so let's say this is section A, okay, so that means because in hole 1 there is only the weight of water A, right? So this is the weight of section A only, right? Because section A is applying a weight, a force onto the downward sections, and keep in mind that fluids exert a force in all directions, right? Because if you know, all molecules inside the water are spreading out in equal direction. They're bumping into the walls, they're bumping into each other, and they're jiggling around in every single direction, right? And because of that, the molecules that are spreading out in this direction, they are going to come out, okay? And because you have the weight of the water over here, then those molecules are going to provide a downward force, which is going to, exert a force outwards as well. It's going to, push the water molecules outwards as well. Okay. But in hole 2, you don't just have the weight of section A, which is pushing you down. You have the weight of section B, which is pushing you down as well, right? So that means that these molecules are going to get a greater outwards push, right? So that means it's going to have the weight of section A plus the weight of section B, right? So that's why the stream is stronger, because all the water molecules above you are pushing you down and outwards as well. Then hole 3. Why is hole 3 having the strongest stream? Because it has not just the weight of section A, not just the weight of section B, but it is withstanding the weight of 3 sections, right? 3 chunks of water, if you want to call it chunks or whatever, right? So that means C is going to get the greatest amount of force from, so gets the greatest amount of force, due to weight of all water molecules above. Okay, so keep in mind that all fluids exert a pressure in every single direction. Okay, right? If you question why do fluids have pressure, and keep in mind, this is not just fluids, not just liquids. Fluids include both gases and both liquids. Okay, gases are kind of like an extreme kind of fluid, but they are also counted as fluids because they have very similar properties. Now, why do fluids have pressure? It's a very simple idea. Because all of these particles, for example, in a balloon, right? You can already see that the particles exert, I'll write that down, fluids exert pressure in all directions. In all directions. Okay, so now that means this balloon, all the particles are jiggling around in every single direction. They're pushing each other. They're pushing the walls of the balloon. And because they're pushing the walls of the balloon, that's why it expands, right? If they don't push on the walls of the balloon, then how is it going to expand, right? It is because the particles were applying a force onto the area of the balloon. That is the reason why they were exerting a pressure, an overall pressure on the walls of the balloon, right? In the same way, a fluid also exerts pressure into the walls of the container and to itself as well, right? So it is simply, why do fluids have pressure? Because of the constant random motion they have. because of their jiggling around and them applying a force onto the area of the wall of the container, whatever, molecules, then fluids naturally have pressure. Okay. Make sense? All good? Okay. Now, pressure in fluids. You can't exactly use pressure is equals to force over area in fluids because, how are you supposed to calculate the pressure of, yeah, let's say at a certain depth using this formula? You can't exactly do that. Like, what force are you supposed to take? What area are you supposed to take? Area is a 2D, dimension. Then how are you supposed to calculate that? Then we have a different unique formula specifically for pressure in fluids. Now, let's derive that. It's pretty simple derivation. If pressure is equals to force per unit area, right? Now, if force or, force is just equal to the weight, you can call that as the weight of the fluid, okay? Because if, for example, if you take this section, okay, if you take this section, then the pressure at this point, right? What is the force being exerted at this point? It is going to be the weight of all of the fluid that is above you, right? So then the force must be the weight of the fluid that is above you. So that means mg divided by the area. Okay. Now, can I write density is equals to mass per unit volume? And instead of writing mass per unit volume, what if I make m the subject, which gives me m is equals to density into volume? Density into volume, right? That's perfectly right. So what I'm going to do is I'm going to replace m with rho g. By the way, keep in mind, we call this density as rho as well. Density slash rho, not the crying wala rho, but rho is often used as the term for density. Now, if mg over a, yes, rho v g over a. Now, what is volume? Isn't volume considered to be the area multiplied by the height, right? And instead of writing volume, can I write area multiplied by height into g over a, right? That means what happens is a and a cancel out, and what are you left with? Then you are left with pressure is equals to rho g h. And I'm sure you've heard this formula many times before in IGCSE, right? So this is density of fluid, okay? G is just, acceleration of gravity. H is the depth, very important, depth in meters. P is the pressure in pascals. Okay, right? So in this formula, you can clearly see three things. Pressure is directly proportional to the density of water. Pressure is directly proportional to G. Pressure is directly proportional to the depth. Now, think about it. Think about why these make sense. If the density of the water or fluid is higher, right, then that means you have overall more molecules in the volume. If you have more molecules there, that means more forces because of the same molecules, right? So clearly pressure would increase. Why does G increase the pressure in fluids? Keep in mind, this is the pressure in fluids. Okay, so pressure in fluids, right? This is due to the pressure. Because of the forces of the molecules and the weight of the fluid, it should equal to rho gh. It is inside the fluids. Okay, that means if you were to go for a swim, then you are going to get a pressure equal to this value because of the forces of water that are pushing on you. Okay, sounds good. Then what else? Oh yes, now if you increase the depth, then pressure is also going to increase. Why? Because think about it, if you go down, right, if you go deeper, then that means you have the weight of all of the molecules above you which are pushing you down. If you go even deeper, then you have even more molecules that are pushing down on you. So that's why pressure on you would also increase then. Now, let's do a few basic calculations. For example, let's say you have a submarine in water, and let's calculate the pressure of this submarine at this step. Oh, my calculator, my precious. Okay, pressure is equals to rho 1000 into G is 9.81, and the depth is in this case 10 meters. So that means this is 98100 pascals. Okay. Let's calculate the pressure at 1000 into 9.81 into 50 meters of depth. So clearly it rose 490,500 pascals. That's a lot. Then if you go to 200 meters, that is extremely, extremely deep, which means this is equal to 1.962 into 10 is per 6 pascal. So that's like 1.2 million pascals at 200 meters of depth. Okay. Any questions up till now?
No.
Yes. Hania, made sense? Kaima?
Yes.
Okay. Okay. I'll be back in 2 minutes and you can write this down if you want. I'll be back in 2 minutes. Okay, let's begin. Now, I am sure some of you remember that in, 2023, there was an OceanGate submarine that imploded, and, there were like 5, 6 people killed. They were like so deep into the ocean. They were trying to get to the Titanic shipwreck, and that exploded. Not exactly exploded, it imploded. Now, there's a difference between imploded and exploded. Explosion means that it exploded outwards, it spread out outwards, right? Imploded means that uh, it was crushed into itself, right? So that means, explosion would mean that something is exploding outwards. Implosion means that it was crushed inwards, right? It's kind of like an inwards explosion, okay? And we're going to calculate how much force was on them. Okay, let's see how we can calculate it. Now, that submarine was at a depth of 3.8 kilometers in the ocean, right? So that's a huge depth. Like 3.8 kilometers is extreme. That's like half the height of Everest, I believe. Now, how can we calculate the pressure due to fluids? We can do that pretty simple. We know that density into G into H is just equals to the pressure due to fluid. Let's check. 1000 into G 9.81 into the depth. The depth was 3,800 meters. Let's check what the pressure on them was at that point. So 1000 into 9.81 into 38000. So that was equals to 337 point. So basically 37 into 10 is per 6 pascals. So that means pressure was equals to 37 million pascals. That is a huge amount of force, 37 million pascals. Now, if you think about it, keep in mind that in fluids, pressure is being exerted from all directions, right? Because particles are in random motion. So that means pressure is being exerted from every single direction. It is being exerted on every single tiny little area patch on you, right? And as you go deeper, right, you have the weight of the fluid above you, and right, and yep, that's it. That's the majority of the extra pressure is because of all of the weight of the fluid above you, right? And as you keep going down, you have a greater length of liquid that is falling onto you. Now, if we knew that the external area of the OceanGate submarine was, so this, if you take up like tiny little patches of areas and you calculate them and you sum them up, it was calculated that their external area of the ship was 85 meters square. Okay. Can we calculate how much force there was on them? Right. So if pressure is equals to rho gh, we figured out, that the pressure on them was 37 million pascals. Okay. And we know that the external area, the area on them, the area of the ship was the area of the ship was 85 meters square. That was like the total surface area of the ship. Okay. Now that means, can you calculate the force on them? Yes, you can. Pressure is equals to force over area. Force is just equals to pressure into area. So that means 87.3 into 10 is power 6 multiplied by 85. So force is equals to into. Wait, 1 second. Okay, yeah. So this is 3.2 into 10 is power 9 newtons. This was the amount of force that was being applied onto them. And if you want to convert that into like more, readable terms, you can convert it into kgs. Wow, you can just do weight is equals to mass mg, and then mass is equals to weight over g. So that means if you divide this by 9.81, it's going to give you a mass reading, right? Because it's more familiar for us to think about forces in terms of mass than newtons. We're not really familiar with newtons. You don't really know what is 5 newtons and 10 newtons and 300 newtons, but we do know, how heavy kgs are. So if you divide this by 9.81, it's going to convert it. Okay. 326 into 10 is per 6 kgs. That means there was a force of 326 million kgs on them, right? So that's a very readable number. So that means this was the amount of weight that was being applied onto them from every single direction. So that means even if you have like a tiny little, a micrometer worth of crack or, leak or, some kind of, pressure difference, the extreme amount of pressure due to the fluid is going to crush them in, 0.0001 seconds. You're not even going to feel it because of the very, very extreme amount of force, right? So, submarines are amazing, but they're also extremely horrific if they go wrong. That's why, they've got to be engineered from the best material in, they've got to be tested under extreme stress conditions, but, something happened. You don't know. Okay. Too dark, man. Okay. Now, let's, make it a bit more, let's make it a bit more lighter. Now, let's move on to another kind of pressure. That is the atmospheric pressure. Now, I'm sure you've tried this somehow, that if you take a can of Coca-Cola or whatever can you want, and you try to suck the air out of it, you literally suck the air out of it. What happens is that it gets crushed, right? Why does it get crushed? Think about it. How does it get crushed? Now, initially, when you haven't sucked the air out of it, then you see that it's not getting crushed because the forces from the outside are being balanced with the forces from the inside, right? Now, these yellow lines are basically, this is the pressure due to air. This is what we call the atmospheric pressure, right? This is the pressure due to air or pressure due to the atmosphere around you, because, even atmosphere has atoms, and those atoms are exerting a constant force onto you. Now, it wasn't being crushed initially because the forces from inside were being balanced out with the forces from outside, right? Right? Because there was an atmospheric pressure in the can as well, right? You had air inside the molecule that was pushing outwards as well. And because of these forces were being balanced, that means that the net force is zero. And if net force is zero, then obviously it would not, collapse. Then what happens when you suck the air out of it? When you suck the air out of it, then the pressure, you have not left any air inside the can, which means that there is nothing pushing the air outwards, right? There is no inward force towards the outside. So that means no inner air pressure remains. Thus, collapses, right? This is basically what imploding means. This is implosion. This is implosion. You've crushed it from the outside because inside the air pressure, inside the air pressure, the was much lesser than outside. Outside, imagine that there was 100 Newton force outside, and because you took out all of the air from inside, then there is no opposite force from the inside. So that would mean that it's going to crush. And by the way, that's almost the same thing that happened to the submarine as well, right? If there is a very, very large amount of force from the outside, then inside the submarine, you have to apply an equal and opposite force to make sure that you do not get crushed by this force. That's why the submarines, and oftentimes if you have any kind of if you want to dive into the ocean, or you want to take something deep into the ocean, then you've got to make sure that the pressure from outside is balanced with the pressure from inside, right? Because if the pressure outside is too high and pressure inside opposing it is not too high, then you're going to get imploded. Okay, so that's a really important distinction that you've got to know. It's because of the pressure difference that you die. Okay, sounds good. And again, why do we have atmospheric pressure? Similar example already studied, that because air is constantly moving around in every single direction, it's constantly hitting around stuff, and it's applying a force onto a certain area, right? So it's applying a force onto you, it's applying a force onto the ground, it's applying a force onto everything you're touching, right? Because of that, there is atmospheric pressure. And another thing, where is it? Right? As you go higher, the atmospheric pressure falls. We often hear that, there is lesser oxygen in mountains, and as you go higher into the mountains, it is difficult to breathe because there is literally lesser amount of air at the top. Because if you think about it, as you go higher, right, most of the air is staying down because the air also has a collective mass, right? And if the air also has a collective mass, then most of the air is being pulled down, right? That's why you could imagine that, that there is a constant blanket of air that is being pushed down towards the earth because of its weight. If you like combine all of the weight of the air, then it is a huge mass. And that means that because of gravity, air is being pulled down, and because of gravity there would naturally be lesser molecules at the top, because the molecules at the top, they would have enough energy to overcome the force of gravity. That's why they're at the top, right? But not all of the molecules would have that much energy. Okay, sounds good. Now, question is, how much is the atmospheric pressure, right? Yes, Anya, do you know how much the atmospheric pressure is? Any idea?
It's 1 times 10 to the power of 5 Pascal.
100,000 pascals is the atmospheric pressure. Now, let's think about what that number means. Aras, do you know what this number means? How do you define this? 100,000 pascals. What do you think? What does this
Is it?
number mean?
It's the force by air.
Exactly. So that means on every 1 meter square patch, there is a force of 100,000 newtons because of air. Because of air. Why? Because all of the particles are jiggling around in random directions, and gravity is also pulling air down towards the earth. So that means when you're standing, there is a weight of all of the air above you, just like in the sea, right? So you could imagine that this is the value of that force on you. Okay, and one other thing. If you think about pressure as, force over area, then you can, use the formula to get the desired ratio you want. Now, we know that this is force over area, right? So that basically means that if pressure is equal to 100,000 pascal, that means that there is 100,000 Newton force per meter square, right? That's basically what pressure means. And you can do that for any amount of pressure you want. Okay. Now the question is, why don't we feel it? What do you think? Why don't we feel this such a heavy amount of force? 100,000 newtons. 100,000 newtons is actually 100,000. Yep. So that's equal to, this is actually equal to 10,204. No, wait 1 second. Yep, yeah, right. That's right. 100,000 divided by 9.81. So that means 10. So roughly 10,000 kg of air per 1 meter square. So that means if you take a patch of 1 meter square, right, then there is going to be the weight of 10,000 kgs of air for every meter square, right? That's basically what it means. Now, if you have such a great amount of mass of air onto you, why don't we feel it? What do you think? Is it because, we're all very extreme bodybuilders and we're so strong? What do you think, Kaima? Any idea? Why don't we feel such a large atmospheric pressure onto us? What about it? What do you think, Anya? Any idea?
No, I'm not sure.
What do you think, Aris? Why don't we feel the pressure of air on us? No idea? Isn't it interesting? If there is so much pressure due to air, why don't we feel it? We can even calculate it. Let's calculate it. For example, let's calculate the force on your hand. Let's assume that your hand is this rectangle. And how about we calculate the amount of force due to air onto your hand? Let's see. Can we calculate that? Yes, we can. Because we know that pressure is equals to force per unit area, right? Now, we know that the pressure is, so force is equals to pressure into area, right? What is the pressure due to air? 100,000 pascals. What is the area of your hand? Can't you just assume that this is a rectangle and multiply length into it? Yes. So that means 15 into 10 to the power minus 2 multiplied by 11 into 10 to the power minus 2. I will calculate the force on your hand, right? Because, this was a large patch of 1 meter square, but your hand is obviously much smaller. It has a smaller area. 100,000 into 15 into 10 to the power minus 2 into 10 into 12 minus 2. 11 into 10 to the power minus 2. Okay. So that means, 1 second. Yep. Okay. So that means 1650 newtons of force. So that means 165 newtons of force is being spread out onto your hand. Now, again, forces, it's much difficult for us to understand how much forces are. So this is roughly equal to 165 kg of force, right? Because that's much more interpretable. Now, think about it. If you have a 165 kgs of force that is being applied onto your hand because of air pressure, then why don't you feel such a large amount of force? And the overall force on your body is even much higher because you have a greater amount of area on your body. So if you keep increasing the patch of area, then that means more force will be over there, right? For example, if you have a large tile, right? The large tile is obviously going to have more force on it because it has a greater amount of area, right? But a smaller tile, it's going to have a much smaller amount of force on it because there's literally lesser area to cover. Okay. Now, why don't we feel this? Why don't we feel this? Or do we feel this? Have we just grown too strong? Yes. Whoever is able to answer this question would get $1 million and has already become a physicist. It's such a simple answer. Yes. Would you like to try or no?
Is it because we feel it equally from all direction?
Exactly. Kaima is the new physicist of the year. That I told you earlier that fluids exert a pressure in all directions, right? So that means if you have the force from upwards, you are going to get the same force from downwards as well, right? If there is a force upwards of 165 kgs, you remember that fluids exert a pressure in all directions, right? So that means the forces cancel out. The forces cancel out, right? So there is a large amount of force on you, but because the upward forces and the downward forces and the leftward forces and the rightward forces cancel out, the forces cancel out. Forces cancel out, right? So you see that, this is this magical act of canceling out happening all around you. And because of that canceling out, you actually do not feel that large amount of pressure. Forces cancel out, thus you don't feel. Okay, excellent. Sounds good. Yes, Aris, does that make sense?
Yeah, it does.
Yes, okay, sounds good. Yes, Anya, all good.
Yeah.
Right. Now, when we were calculating the submarine's pressure, what is the total pressure at 3,800 meters? Now, we calculated just the pressure due to fluid. Now, on that fluid, you have this atmosphere above you as well, right? And that atmosphere is going to push down onto the fluid as well, right? Imagine, like two blankets onto each other. If Over here, you have the pressure due to fluid, right? The weight of all of the fluid above you. But above that, you also have the air which is pushing the fluid down. You imagine, like, you're pushing the fluid down with your hand. That is going to press down the submarine as well. So if you were to calculate the total pressure at any position, the total pressure is always in fluids. Sorry, if you're in the ocean, you're going to add the atmospheric pressure plus the pressure due to fluids, right? So that means you have to add 100,000 pascals as well as the pressure due to the fluid itself, which was that was 37 million, right? But 37 million plus 100,000 is like barely nothing. 37 million pascals, right? So this is the total pressure onto the fluid. You have to account for atmospheric pressure as well. Okay. Now, I'll wait for you to solve this question, right? So you've got to calculate what the pressure on this person is at this point. Okay. The density of water has been given, and you have to calculate the total pressure exerted on the diver. Okay, I'll be back in 2 to 3 minutes. It's a pretty simple question. You just have to use the formula. Okay. Yes. Anya, what number did you get?
I wrote my answer in standard form, so I
Okay.
got 5.32 times 10 to the power of 5 pascals.
10 to the power 5 pascals. Okay. What about you, Ariz?
I actually got
Hmm.
4.3 into 10 to the power 4.32 into 10 to the power
Okay.
5 Pascal.
Okay. What about you, Kaima?
I got 5.4 times 10 to the power 5.
Okay. So close enough. 5.4. Okay. Now, they're fairly different, but let's check what could be the reason. Now, if you are asked to calculate the total pressure exerted on the diverter, total pressure means that you have to add atmospheric pressure as well, which is equals to 100,000 pascals, right? And you've got to know that. You've got to like memorize that, unless they give another value to you. Okay. Now, what is the pressure at this point? Pressure due to total pressure is equals to the pressure due to atmospheric pressure plus the pressure due to the fluid. Okay. Now, atmospheric pressure is just 100,000. But what is the pressure due to fluid? It's just rho times g times h. Rho is 1100. What is g? 9.81. But what is the depth in this case? The depth is actually supposed to be from the top, right? When you look, when you know you dip yourself into the ocean or something, you look at how deep it is from the surface, right? You don't look at, for example, when you dip your toe into the ocean or the sea, whatever, you talk about you're 2 meters deep into the surface. You don't talk about I am 300 miles above the surface bed. You don't really talk about that, right? So generally we take the depth as from the surface. So you've got to calculate this value. This is the depth. Okay. So that means what is this depth going to be? So if 100 meters is the total length, 60 meters is this. So that means this must be 40, right? Okay. So that means H is actually 40 meters. So this is supposed to be 40 meters. Okay, let's check. So 100,000 plus 1100 into 9.81 into 40. Yep. So it's actually 5.32 into 10 raised to power 5 Pascal. So yes, Hania, your answer was right. This is the total pressure, right? So whenever you hear the word total, be careful. Ariz, I'm pretty sure you didn't add atmospheric pressure, right?
Yeah.
Yes? Okay. So make sure you add that. That's a very common mistake to make. Okay. Okay. Sounds good. All right. We have covered 80% of density and pressure. Okay. The next topic we have is upthrust. Okay. And upthrust is a slightly complicated topic. Up till now, we've just been like doing some IGCSE concepts with a few A level, flavors, but it was all pretty easy, all basic stuff. But, this understanding is important to solving the next one. Now, the question is, hmm, have you ever studied upthrust before? Yes, Aris. Have you done that in school?
I have, but
Uh,
I didn't really understand it that well.
and you don't understandable. It's very difficult to understand, if not taught the right way. Yes, Kaima, have you learned about upthrust before at school?
Yeah.
You have? Did you get any of it or no?
Mm, yeah, like quite, not but not much.
Hmm. Okay. Can you tell me what it is? What do you think? What do you remember about it? It's fine if it's different. Don't worry. Even the rest of us don't know what upthrust is. What do you think? What do you remember about upthrust? What is it even about?
Like is the like upward force like exerted by like a fluid
Yes, that's right.
object?
That's right. That's absolutely right. Yes, Anya. Have you studied upthrust?
Yeah, but I didn't get it.
You didn't get it. I'm sure you did like some kind of derivation as well, or no?
Yeah, we did like a lot about it.
Hmm. Okay. Okay. Now, Okay. Now, upthrust is pretty confusing if not taught the right way. Okay. Let's approach this question by a very simple question. Why do some objects float and some sink? Let's start from this question. It's much easier to understand it if you start from this question. I'm sure, you've you know a little bit of this, ever since you were a child. Why do some objects float and some sink? What do you think the answer is to that? What is like the ultimate answer? What do you think?
Some objects are like more dense or less dense.
Ah, exactly. It depends upon the density of fluid versus density of object. Okay, it depends upon these two things. Okay, but if you were to zoom in a bit more, okay, in reality, what happens is that density does play a very important role, right? If you talk about the ultimate effect, everything else cancels out, and you see that it is only the density which is going to determine whether something is going to sink or float. Okay, we will try not to do the entire derivation today, but I'm going to show it to you in a nice way. Okay, now the density of the fluid versus the density of the object. If you zoom in a bit more, right? If you like zoom in a bit more and look into a bit more physics, then it is basically in reality, this is also correct. In reality, it is the net force between upthrust and weight. That's it. That means if something is going to, float or sink, it's going to just be the forces that are going to determine that, right? It's the upthrust which is going to determine that, and the weight of the object that's going to determine that, right? And then you acknowledge that what is the weight of an object and what is the upthrust, okay? But then you have to figure out, what does upthrust depend upon? What does upthrust depend upon? That's another question, right? So you're into the chain of questions. That density of fluids, that just really means that net force between upthrust and weight, right? We know the weight is just dependent upon whatever the mass is and g is. But what is upthrust? How does upthrust is even calculated? What is upthrust? Where does it come from? And why does it exist, right? So what does upthrust depend upon, and how does it arise? How does it arise? Okay, we'll go towards the animation first. The nice one. Check this out. Hurry up. Okay, I believe. Okay, now check this out. If you look at this object, there are two forces, right? I'm going to disable all of them right now. Okay, now you have, for example, this block, okay? And for example, if you take it out, okay, now the liquid is 100 liters. But what happens as you submerged it? You check that the volume is displaced, right? There is an increase in the volume because you had to accommodate for the extra fluid because of the volume of the object that was submerged. There is a force of gravity onto the block, and there is an upward force from the fluid, which is what we call the upthrust force, or we also call it the buoyant force. Now, only a little bit of the fluid, only a little bit of the block is submerged. Notice what happens as I increase the density of this block. I'm going to increase the density of this block. If you notice what happens, one second. Right? As I'm increasing the mass of the, no wait, oh, I've got to change the density 1 second. Okay. Can I change? Okay, yes. So notice what happens as I keep increasing the mass. Okay. Yes, as I keep increasing the mass, this means that the density of the block is increasing. And as the density of the block is increasing, it is sinking even more and more and more and more, right? The weight is increasing, but so is the upthrust, right? The blue arrow is the upthrust, and it is constantly increasing. It keeps increasing. And right now, there will come a point over here. Okay, now at this point, do you see that the density of the fluid is exactly equal to the density of the block? Now, what happens is, imagine if I increase the density of the block even more, and that's it, it sinks. Now, in this case, do you see that the weight is much greater than the upthrust? Now, upthrust was initially increasing, right? It was initially increasing, but after a certain point, it stopped increasing, and the weight was just too much for the upthrust. Okay, the weight was just too much for the upthrust. Now, for example, if I increase the density of the fluid, then I see that again the upthrust is increasing, right? If I, oh my god, right? Let's slingshot it out. I slingshot it out. Why? Because again, in this case, the density of the fluid is 3, whereas the density of the block is 1, right? Now, because the fluid is more dense, right? Or the object is less dense than the water, that means it's not going to sink, it's going to float. But if in this case, the object is more dense than the fluid, then obviously it's going to sink, because if you take the resultant forces, it is accelerating downwards. Okay, sounds good. Okay, now what is determining these blue forces? Oh, sorry, these blue forces and these, upthrust forces. And you noticed over here on the left side that there is a fluid displaced parameter as well, right? On over here on the left side. You see that as I take out the block, the fluid displaced is 0, because there is no fluid extra displaced. But as the object is into the fluid increased in volume, right? By 4 liters. And notice something interesting, that the upthrust force, the upward blue force, is exactly equal to the weight of the fluid that was displaced. I'm going to repeat that. Notice an interesting connection, that the pink arrow is the upthrust on the block, right? Now that pink arrow upthrust is equal to the weight of the fluid that you displace. You can read that on the left side, that if you measure the amount of fluid that was displaced of 4 liters, the weight of that fluid is 39.2 newtons. How is it that these two are connected? How is it that the block which had an upward force, okay, that upward force is equal to the weight of the fluid that was displaced? This was one of the most important discoveries, I don't know how many centuries ago, and this was the idea of Archimedes. The buoyancy idea came from this guy, where he said that the upthrust on an object is equal to the weight of the fluid displaced. Don't worry, we'll break these down step by step. Right now, I'm just exposing you to all of the ideas that, to get you interested into the idea, right? And as I keep increasing for example, what is it? For example, can I see this over here? As I keep increasing the mass, I see, you notice it again, that, weight is higher and upthrust is also higher, but the fluid displaced is more, right? The fluid displaced is more as well. And do you notice that the upthrust value on the block is exactly equal to the weight of the fluid that you displaced? Again, pretty interesting. How does that happen? Okay. And you can do other things as well. You can increase the density of the fluid. And if you keep increasing the density of the fluid over here, because the fluid is more dense than the object, it's not exactly sinking. But if I increase the density of the block, again, it is going to sink. Okay. Now, we're going to, we're not going to exactly complete this today, but I'm going to expose you to a little bit of the ideas. Okay. Now, any questions, by the way? Any questions, by the way, which I should keep in mind when answering all of them? Yes, Aris.
No.
Okay. Yes, Hania, Kaima?
No.
No. Okay. Now, let's see. Upthrust, how is upthrust even formed? Where does it originate from? Why is there an upward force? We'll just talk about that today, and we will do the rest of the questions and the derivations later on. Now, if you have a block, now this block has a mass m naught. Okay, we're defining the variable that we're taking right now. Okay, it has an area. It has an area a naught, and it has a certain height h. Okay, then what would be equal to the volume? The volume is what we call V naught. This is VO, all right? So this is object O. Okay. And then it has volume V naught, which is basically equal to A naught multiplied by the height. Okay. And it has a density. It has a density which is equal to rho naught, which is basically the same as M naught over V naught, right? Mass over volume. Okay. Now, if you take the fluid, okay, if you take the fluid, if you submerge that into the fluid, if you submerge into the fluid. Now, when you submerged it, there is only one thing that is going to happen right now. That because you submerged this block into water, okay, forget the arrows and stuff. Because you submerge this block into water, then there is going to be a volume of fluid displaced, right? And this is going to exactly be equal to, in this case, volume of fluid displaced is equal to volume V naught of block if fully submerged only, right? Because if it's not fully submerged, then only the submerged part would be the fluid displaced, if fully submerged. Okay. Then, where does upthrust come from? Now, listen very carefully. If you remember, what was the pressure at this height? So, for example, one second. Okay, yes. So, this is like the new volume when it's submerged. If this is the height h1, do you remember what the pressure at a larger height was, at height h1 due to fluid? It was rho, density of the fluid, multiplied by g, multiplied by depth h1, right? So that means at this height or at this depth, rho gh is going to be the pressure due to the weight of the fluid and all the motions. Okay. What is going to be the pressure on the base? P2. Now, do you see that the pressure on the base is going to naturally be higher because it is at a higher depth, right? Because we know that as the depth increases, right, the weight of the fluid above you is also going to increase, and fluids exert a force in all directions, right? Again, I'm going to write that down again. Fluids exert force in all direction. In all directions. That's like literally the most important thing about pressure in fluids. Okay. Then, what would be the pressure due to height h2? It's going to be again density of the fluid multiplied by g multiplied by h2, right? Now, this is basically the force. These red arrows are the force due to the top part of the water, right? Or you could imagine this is the force at depth h1. And these red arrows are the forces due to depth h2. Okay. Now what happens to the sideways forces? The sideways forces actually cancel out. Why? Because think about it. If you keep increasing in depth, obviously these forces keep increasing. 5 Newton, 7 Newton, let's say, 5 Newton, 7 Newton, 8 Newton, 9 Newton, 10 Newton. But do you see that it also increases from the left side? 5 Newton, 7 Newton, 8, 9, and 10. So clearly we see that the sideways forces due to water cancel out. Sideways forces cancel out. Okay. Yes. Are you following me so far? Yes. So far. Okay. Now, if P2 is the pressure, I'll write that down. This is pressure due to fluid at depth H2. Okay. Whereas this yellow is pressure due to fluid at depth H2, at H1. Okay. Now, think about it. If P1 is equal to rho g H1, P2 is equal to rho g H2. We know that density in G is the same, right? If you look about depth, since H2 is always greater than H1, right? Because it's at a greater depth, right? That means then P2 must be greater than P1, right? So that means that's an extremely important implication. That means bottom face will get larger force, will get larger force. That's an extremely important, implication. That because the pressure is greater at the bottom face compared to the upward face, the top face, the pressure due to the downward face is going to be much larger. Okay, I'm going to write down the forces as well now. Okay, now let's zoom in a bit more. This, the top face is at a depth of h1. Okay, and the bottom face is at a depth of h2. We're going to ignore the sideway forces because they just cancel out. They keep increasing as well, but as they keep increasing, it keeps increasing on all sides. So the sideway forces cancel out. It is only the top and the bottom forces that don't cancel out, right? So keep in mind, top and bottom force don't cancel out. Okay, now there is a top force which we're going to call F1. What is this top force? That is basically the force due to the pressure of water on top of you. And there is going to be a much greater force, F2. There is going to be a much greater force, F2, onto the bottom of the force, bottom of the face, right? Why? Because because at the bottom there is a greater pressure, then that must mean there must be a greater force. Okay. Can we calculate how much this force is? Yes, we can. So again, what was the pressure at depth H1? P1 was equals to density of fluid times G times H1. Okay. And what was the pressure P2 at the bottom of the face? Rho F into G into H2. This means fluid. Okay. Can we write that? Can we calculate the force? Yes, we can. Can't we just say that P1 is equals to force per unit area? Yes, we can. Then that means this is equals to rho GH1. Okay. And so let's call this F1, right? Because, P1 is equal to F1 over A, right? This is the force over the top area. Okay. This was A naught, the area of the top face of the bottom or the bottom face. Now, if F1 is this, can we multiply A naught on the other side? Yes, you can. F1 is equals to rho fluid into G into H1 into A. Okay. Do you remember what this was? Area into height is what? Isn't that just volume? Exactly. So that means the top force is going to equal to density of fluid multiplied by G multiplied by F. Sorry, volume. Okay. Now this is the volume. Oh, in fact, you know what? Let's skip this part right now. Okay, I'll get to that later on. Okay. And then what is pressure P2? Pressure P2 is just again, F2 over area, which is equals to this same thing. Okay. Then, if you want to calculate the force F2, this should equal to this entire value and you multiply it again with area. You multiply it again with area A naught. Okay. Now you can clearly see that everything else is the same, right? Everything else is the same. Only H2 and H1 are different, right? I can clearly see from these two expressions that since H2 is greater than H1, F2 will always be greater uh, than F1. That means because of the pressure difference, between top face and bottom face, there is always a net force. There is always a net force upwards. And that net force is what we call upthrust. Okay. Now, I'm going to make it a bit simpler now. We will, don't worry, we will simplify these expressions in a bit. In fact, let's just not do it right now. I'm just going to explain the idea. So then, you can write this down later on, and then you can absorb the idea, and then we can do that in the next class. Now, at the top face, we know that pressure is smaller, right? Which means there must be force F1, which is small because the depth is smaller. But at a greater depth, the pressure is higher, right? Then that must mean there would be a greater force upwards equal to F2, right? So F1 is at depth H1 and F2 is at depth H2, right? Now, because the depth is greater at the bottom, then that must mean there is always going to be a greater force from downwards, right? So if you subtract F2 minus F1, this is equal to upthrust. This is the net upward force. How do you define upthrust? Definition is going to be, this is the net is an important word, net upward force on object due to, or object submerged due to pressure difference between top and bottom. Okay. Yes. So because there is an upward force and there's a downward force, and F2 is always going to be greater than F1 because of the height difference, right? That must mean F2 will always be greater and F1 will always be smaller. And if F2 is always greater, right, then that means if you take the net force, right, the net force is this value, F up. And this F up thrust is basically the resultant forces between these two because the upward force is always going to be greater. This is basically F2 minus F1. Okay, right? We're almost there. We just have to get to the result, but I think, that's all for today. We've done quite a lot of stuff. We've done like 1, 2, 3, 4, 5, 6. I don't know. Damn, we've done 18 pages. Wow, guys. Congratulations. It's finally over. Almost over. Okay. I have stopped